So let's pick up our story here. That what we're really looking for when we're trying to invert a matrix, if we're trying to invert A, is we would like to be able to solve AX equals B just by multiplying on the left by this inverse matrix, A inverse. And that will be a successful thing to do exactly when multiplication by A inverse succeeds in completely canceling out A. And when it completely cancels out A, it gets us a matrix that when you multiply it by a vector, doesn't change that vector at all. In other words, it gets us the identity matrix. So that's our definition. And if there's any justice, it should actually also thwart our non-commutativity a little bit, in the sense that the inverse of the matrix should cancel out A when we multiply on the left, as we've done here, but it should also cancel out A when we multiply on the right by it. So the definition of an inverse matrix, oops, too far. So the definition of A inverse is that when I multiply this matrix by A, on either side, I should get the identity matrix. So A times A inverse had better be the identity matrix, and likewise, A inverse times A had better be the identity matrix. So that's what we're shooting for. So if you have a matrix and you're wandering around the streets of Bridgewater, and someone comes up to you on the street with another matrix and says, hey, this is the inverse of yours. How do you test that hypothesis? Just multiply your matrix and their matrix. And if what they're saying is true, if their matrix is the inverse of yours, then that product, whichever way you do it, should give you the identity matrix. This is the most important definition of the day because it's going to tell us where to start in our search for how to find the inverse of a matrix A. It's also going to tell us how to compute an inverse for a matrix A, because what we end up doing is we end up treating this inverse matrix as an unknown vector in a vector equation. Each column, I should say, of A inverse is being treated as an unknown vector in a vector equation. And then we just have to solve that vector equation. Except we're going to have to solve it as many times as A inverse has columns. So we really get a bunch of vector equations to solve, and those vector equations give us the columns of A inverse. So that's where we're going with all this. And what we wanted to do with this real quick is to prove Theorem 2.2 up here at the top of the page, that the inverse of a transpose of a matrix is equal to the transpose of the inverse of a matrix. And all we have to prove this is our definition for what it means for a matrix to have an inverse, and also this theorem here, Theorem 2.1, that tells us how to take the transpose of a product of two matrices. So with these two things in our back pocket, let's quickly outline a proof of this theorem, and then we'll go back to your reading responses. So again, let's get the statement of what we're trying to prove down here. I'm going to add a hypothesis. If A is invertible, so if A is an invertible matrix, then so is A transpose. We kind of have to say that because then it allows us to write on the next line that the inverse of A transpose, otherwise we couldn't write this thing that I just wrote, A transpose quantity inverse. We couldn't write that unless we were convinced already that A transpose was invertible, which is something we're going to have to prove. But actually, showing that this formula works is equivalent to proving that the transpose is invertible. But the content then of the remainder of the theorem is that the inverse of the transpose is the same thing as the transpose of the inverse. So let's prove that. And again, the two ingredients that we need, I'll keep over here. And the ingredients are, first of all, that when I multiply two matrices and then take their transpose, I get the product of their transposes in the opposite order. And the second ingredient is that when I multiply a matrix by its inverse, whichever side I multiply it on, I do not write A, because I don't want to get too confused here. Let me write it as M. So if I multiply a matrix M by its inverse, whether I do that multiplication on the right or whether I do that multiplication on the left, either way gives me the identity matrix. So there are our two ingredients. Now let's unpack the claim that we have up here on the top. The claim is that this matrix, A transpose, has an inverse, and that its inverse has this form. So inverse is inverse transpose. That's the claim. And so to test that claim, it's as though I'm wandering around in the streets of Bridgewater and I have A transpose, and someone comes up to me and says, hey, I've got your inverse, and they hand me this thing over here on the right. They hand me the transpose of the inverse of my original matrix. And so to test that, we just need to apply this test, our definition of invertibility. So let's, just for the sake of notation, let's call A transpose M, just so that we can match it up with what we have over on the left. And I'll write as part of my proof, let M equal A transpose. Then what we want to show is that M multiplied by this thing, multiplied by A inverse transpose, is equal to the identity. Because then A inverse transpose will be the inverse that we were looking for. Okay. And I suppose it should also work in the opposite order, so let's get both of those down. M multiplied on the left by A inverse transpose should also be the identity. So we have reduced it all down to just two equations that we have to prove. So let's take the left-hand side of each of those equations and see what happens. M times A inverse transpose. Remembering that M is A transpose inverse. Well, we need some way of getting our A and our A inverse together. That's the only way we're going to make any of this any simpler. Yeah? Sorry about that. So M is A transpose, and we want to be able to somehow get A and A inverse together. But take a look at what we're looking at here. We're looking at the product of the transpose of one matrix and the transpose of another matrix. A transpose times A inverse transpose, which looks an awful lot like the right-hand side of our first statement up here. Right? I have the inverse of the transpose of one matrix times the transpose of another matrix. So according to that fact, so now I'm going to use this fact over here. We can rewrite this as a product transpose of a single product. There we go. Namely, what single product can I rewrite it as the transpose of? Try to be as careful as we can here. So if our first matrix was A transpose, then that's playing the role of this factor in our equation. And when we go from right to left, that factor ends up second inside the parentheses. So my A transpose ends up right here. My A ends up right there. And then my second factor, A inverse, is right here on the right-hand side, which means it ends up on the left-hand side on the inside of the parentheses. So here I end up with A inverse. Maybe it would help if I deleted some parentheses to make this connection maybe a little more obvious, just to declutter this expression a little bit. So here I have the transpose of A times the transpose of A inverse. But according to this statement, reading it from right to left, the transpose of A times the transpose of A inverse should be equal to the transpose of A inverse times A, because the product of transposes is the transpose of the opposite product. But what is A inverse times A? That's according to this statement. A inverse times A is what matrix? It's the identity matrix. So we're looking here at the identity matrix transposed. But what do you get when you transpose the identity matrix? Remember, what does the identity matrix look like? It starts with a 1, and then the rest of that column is all zeros. The rest of that row is all zeros. And then the next column, you start with a 1, and the rest of that's all zeros. 1, and the rest of that's all zeros. The lower right-hand corner, you have a 1. So this is the 4x4 identity matrix. What do you get when you transpose that? So what used to be the first row now becomes the first column. 1, 0, 0, 0. What used to be the second row now becomes the second column. It's exactly the same thing. So the identity matrix doesn't care if you transpose it or not. It gives you the same thing. So to finish our thought here, the identity matrix transposed is just equal to the identity matrix. And now reading from the left end to the right end, we've shown that A transpose, when multiplied by A inverse transpose, gives us the identity matrix. That proves that the transpose of A inverse is the inverse of A transpose. And the other product works the other way. So to prove that one matrix is the inverse of another, just multiply them together and verify that you get the identity matrix out of that product. And here we didn't have to do any explicit computation for that matrix multiplication. We're about to talk about that step. This is kind of an abstract proof. So this is how we can use these ideas about multiplication, transpose, and invertibility to come up with a proof in this case.